So today I wanted to talk about world models for AI. You might have heard about a lot about world models, startup companies doing world models, even the big tech companies like Google and so forth, Nvidia making world models. So what are they? How they built, and how do people use them? Okay. Okay, so what are world models, types of models, architectures, some examples, limitations or challenges, and future directions. So what are world models? So they are like internal representations or simulations that AI systems build for their environment. The starting point is that even us humans, we have world models in our mind, right? You have representation of our world, of environment, how our environment works, how it's going to change. For the environment today, the environment in 1 minute, in 1 second, 1 minute, 1 hour, and next day. We have some ideas. We can simulate the world around us, right? So in the morning, we expect the sun to see the sun in the sky. In the evening, to have a sunset, to have no sun at night. So this is kind of world models that you have in our mind. Not only that, but we have also a model of how we impact our environment, right? If I have a glass on the table and uh, I touch it with my hand very quickly, I might drop the glass on the table, right? And I will probably anticipate that too, right? So this is also part of a world model. So it's like really like a mental map, right? So it works for humans but also for AI, or simulated reality that an AI maintains to understand how the world works. Okay. So such a world model allows the AI to predict what will happen next given certain actions, right? So I gave the example of a glass of water on the table, right? If I hit the glass, it falls, so I expect the glass to fall and the water to spill, right? Simulate different scenarios mentally, right? So maybe if I don't hit the glass, but I take the glass gently, it's not going to fall, right? So these are different scenarios. Understand cause and effect relationship, right? So in the case of the for the glass, I hit the glass with my hand, it's going to fall. So the hand is causing the fall of the glass. And also, ideally, learn from limited data by generating a synthetic experience. Right? So this is very useful for robotics, where experimenting on a real environment is going to be very expensive or very slow. So the idea is to generate synthetic world models to learn new behavior. Right? So a world model has typically three components. First is the latent state representation, right? So, so the AI compresses observations like images. So images would be a set of pixels. So the resolution of height and width of the image, and the different colors of the pixel and so on. So, but these are it can be represented as a matrix, as a tensor. And but we want to summarize the image in into fewer variables. This is what we call the latent states that capture the essential structure of that image of that environment, right? So for instance, you have an image full of the color of red. It doesn't make sense to they say label each pixel as red, right? And have a huge matrix to have red, because maybe the information could be the picture is red, should be enough, right? Second component would be a dynamic model. So try to predict the components. So ideally the states, how they're going to change over time, or how they're going to change given some actions. Okay. And then a third component would be a generative model they will reconstruct observations from latent states, right? So allowing the AI to hallucinate or imagine or create possible future scenarios, right? So for instance, you have a world model, and you can ask the AI, what's going to happen if I do this or do action A or action B, right? So if depending on the action A or B, is going to generate a different world, right? Or if you let's say you're into a maze, and you say, okay, what's going to happen if I turn left versus I turn right? I'll go straight, and you have different reconstruction happening on the world model. So here, more formally, so the world model is description of the environment or the current states with an S. It's a future dynamics. So usually the dynamics would be modeled as transition probabilities, right, from one state to the for other states. So based on current states and the action performed by the agents, it could be yourself or other agents in that world, right? So usually we have notation, the state of vector S, action of control signal, the vector A, and future states are S prime at time T prime, right? Suppose today we are T0 at time T, right? So world model is a transition probability P, so that given S and A, right? Give the probability of the future state S prime, right? So S can be a video frame, can be a picture, can be a sequence of pictures, right? So it could be different things. It could be also a 3D picture if you have that. The future states can be at different time horizons, right? It could be the next second, the next minute, the next day, the next week, the next year, or longer, right? You can choose that. And usually the world model is to uncover that probability P, the model, the dynamic, parameterized by coefficient vector theta, right? And theta will typically be the coefficients of the neural networks, right? So they'd use deep neural networks to do that. So here you see the example of a cat, right? So it's not the hair, it's the hand. So the cat is is looking at that vase, and is going to hit the vase, and everything is going to break. So you want the world model to be able to predict that, right? Given that the cat is there, is going to hit the vase, and it's going to break, right? And ideally, the world model being to generate the second picture. So there are different types of world models. The simple models would be to predict next frame in a video, can be used in reinforcement learning. We'll see some example of that. Could be, for instance, for video games, right? Could be for video games, for Atari video games. Could be I know, play Space Invader, and what's going to be the next frame, or the prediction of the next frame. So you see the spaceship coming, or the missiles shooting, and so on. You have hierarchical models when you have different level of abstraction, right? Maybe higher levels will handle long-term goals, on shorter, like lower levels will handle immediate dynamics, right? So it's be like strategic versus tactical, for instance, right? Or lower level would be more like pure physics, and higher level we take into account like long-term actions and so on. You see that many models are going to be latent variable models. So they're probabilistic latent variables, diffusion models, variational autoencoder, GANs, and so on. I will capture the uncertainty of these variables. Right? So very often when you generate a new image, you don't get exactly the same one. Right? This is one of the reasons why it is the case. And then you have like causal models. So causal models, not all the models are causal, in fact, but where you want to explicitly model the causal relationship between two things, an action and a consequence. And ideally, we'll be able to distinguish between correlation and causation, which is not always trivial, right? And this will enable what we say counterfactual reasoning, right? Meaning that we do a different hypothesis. Instead of doing action A, I do action B. What's going to happen? So as we say, it is a counterfactual. Or even instead of take the door on the left, I take the door on the right. What's going to happen to me? So there are different architectures. So we talk about latent models. So we encode the observations into compact latent states. So this is kind of the very common way to do it. And we model the dynamics of these latent states and latent space, for instance, with recurrent neural networks, RNN. The first example would be like that. So it's called like fully differentiable imaginations, means that you can able to solve by usually like backward propagation, for instance. Transformer-based model. So it's like the modern models are using like transformer-based model, but it's what is the technology underlying all the current LLM or VLM, visual language models, and visual language action models, and so on. Most of them are transformer-based. You have also diffusion models. I think we talked about these diffusion models, I think, in the module on robotics. These diffusion models are also able to generate very like photorealistic and physically consistent video rollouts, right, and images of rollouts. So it's very useful, right, to create world models. And then LLMs can be interpreted as world models. They have a lot of knowledge, right? Because they have all the knowledge of the internet, and you can ask in natural language what's going to happen. So it might not be answering you with an image, but a description, right? You can say, and this can be useful for other kind of reality, which is like non-physical. Let's say in economics, let's say if the Fed is not is cutting rates, what's going to happen to inflation? Well, then the LLM will tell you what's going to happen without drawing a picture. Uh, so what are the benefits of world models? So there's what we call a sample efficiency. Right? So ideally, we can use it in simulations so that we don't have to rely on too many like real-world experience, which are usually very costly or sometimes impossible. Uh, ideally, they should be robust and be able to answer what-if scenarios. They they be able to use a transfer learning. So one knowledge that you learn with one task, transfer it to another task, for instance. For instance, if you one model learns to navigate a maze, so navigation should be able to navigate into any maze, for instance. Right? Planning, so can explore action consequences before acting, maybe on a longer horizon. And causality, right? So as we say, to distinguish between correlation from causation. So here, this is the first example. So this is like an earlier model. This is from 2018. So this is like from so the one is the co-author was I think at Google DeepMind, and the other one is a German academic. So here you see that they have a world model with these different modules. So the idea is to predict future states, right, based on the current actions on observations, right. So here I think it's kind of a Doom style of environment, like the video game. So it's a kind of a maze. So each agents can learn what they call like in their own dream. So I can imagine like a simulated environment, right? And then there's a world model that handles the learnings, and there's a controller, right? And the controller and the policy means that you can navigate, right? You can choose to turn. So this is the action. You turn left, you turn right, so you navigate the maze. So it's a bit like in a video game, right? So the agent here in this paper is trained itself in that simulated environment generated by the world models, right? So it trains, it takes different actions, and then you can look at the consequences of his action and learning from it, right? So they're like the three module. There's a vision, right? So the agent can see the environments, is that the observations. There's a memory module, right? Then So the vision model also like is compressing, right, into observation the images into a latent space, and what they're calling is what you see here, right? Is the image goes into a VAE, a variation autoencoder, trying to compress, right, and then transform these images into like state variables. Okay, so this is the vision part. Okay, the V. And then you have a second module is the memory module. So it predicts a future states, right? Future latent vectors using RN. I won't go into details. It's the same idea for RN, but it's RN with a mixture density networks, right? So he tries also to predict some latent. So the H is the parameters of this RNN, right? And then it goes. So this state goes into the controller. The actions taken by the agents, C, right? Maps to the state to actions. As usually, it could be a simpler model, it could be a linear model, linear versus with respect to Z and H, right? And then you have feedbacks, right? So then you move around the maze, right? You face a different environment, you see different kind of image, right? Right? You turn left or turn right, the image will be different. Then it goes again into that loop. Okay. So this kind of earlier model is using RNN. Modern models don't use RNN anymore. Right? So it's like language models use some model. Earlier model would use RNN, but everything has been replaced by transformers. So here, this model is a bit more recent. It's called like Dreamer. I think it's more also from people from some of these people are from Google DeepMind, I think. So also here the idea is to so here it is in simulated environment. So the model is called Dreamer. So he learns a world model from experience, right? That summarizes the agent's knowledge about the environment in the compact latent space. So you have also the idea of latent space, right? So behaviors are learned by imagining trajectories in this latent space. And then the learning is done by back propagation, like in deep in deep learning with different with this imaging trajectory, right? So there's so here there's so inspired by this is truly it's a kind of reinforcement learning. So it's a representation model, right? So we encode the observations, the images, right? What you see, the environment, and the actions, right? So the transition model is the P, right, that we saw earlier. Try to predict the future states, the future transition, how the world is going to change, and then for because it's reinforcement learning, we also try to predict the reward, right? So what reward is going to get by pursuing these different actions, right? So here, these are different challenges. So you might have seen videos of this. So this is like kind of one leg and trying to move forward. So using to jump, well, jump forward. One like two legs running, or like this is like a spider moving across the board, right? So it's learning the environment and learning the actions, and then there's a feedback loop, right? So it's a kind of dreaming of the environment. So here there's a bit more details on Dreamer. Well, so there's like so here it works on the action-critic model. So this is very typical for reinforcement learning. So you have action models that design the policy, right? So predict the actions of what policy to follow to maximize the future rewards, right? We call here the imagined rewards, and the value. So this is what we call this is the critic. You estimate the expected reward, right? Beyond the imagination horizon, right? So you have the policy, so the actor acting, and then you have the critic module or the value model tells you, okay, if you pursue that sequence of action, how much you are expected to receive, right? So this model has different advantages. It's a long horizon model, so long horizon planning, right? So it consider rewards beyond the short imagination horizon. is relatively like data efficient, right? Because there's a modeling of the environment. It's not what we call like model-free agent. Model-free agent means that they don't bother modeling the environment, right? They just look at reward, right, and learn from it, right? Action, reward, and learning from it. There's no attempt to model to model the environment. So fast computation and better performance versus older model. Okay. So MuZero is, you might be surprised to see that. So this is a reinforcement learning model, but it's also like a kind of world model, right? So it's trying to learn a model. So here these are games. So it is different games, but typically be like Atari video games. So some of you might have like done these games are like popular in the 80s, so kind of a long time ago. But the Atari games with Pac-Man, Space Invaders, and so it'd be like 2D games, like no, not a very high resolution. So what MuZero allows to do, so it's model-based reinforcement learning, is try to learn these games only by trial and error, right? So there's no explicit programming of the rules of the games. I mean, there's programming of what you're allowed to do, right? You cannot have you play outside the screen and these kind of things. But there's no you're not teaching the strategy. It's not trained on human playing the games, for instance, right? So it's really like MuZero. Zero means that there's no like almost like I know it's like exactly means that's like a zero prior, right? So these the same idea as if you remember, you have AlphaGo and AlphaZero for to play Go. So AlphaGo was initially trained on human playing on champion like very good players playing Go and trying to learn from it. And AlphaGo like gave up on training on human examples. Yeah. So, so here there are like three components, right? So it's kind of similar to what you've seen before. Representation functions. So encode the observations into hidden states or latent states, right? So dynamic functions here again. So predict future rewards given the states and the actions, right? So it's similar to what we've seen. And prediction functions to compute the action selection, right? And the future rewards. So how you are going to suppose to play this video game. So one thing that is interesting is the illustration here is trying to calculate the value functions. What is the value of a position of a future action, right? So try to move forward, kind of simulated, and this is what we call tree-based search, right? And when it's done across like multiple like scenarios, it's a Monte Carlo tree search. Okay, but the idea is to get a value function, and then you choose the action that provides the highest value. Right? There are different actions that say, okay, A1 will give me the highest value versus A2, for instance. Okay. So this is more goes more into details. Maybe I'll skip that. Just to mention, yeah. So here you mentioned the acting is use Monte Carlo tree search, right, to select the actions. The training is done by backpropagation. So all these module of policy value, they're all like based on neural networks. So you need backpropagation to recalculate these networks. Okay. Um, um, okay, let's rotate a bit. I think. Okay, so it wants me to. Okay, my computer is overloading a little bit. Okay. Okay, so now this is I think, yeah, this is the next page. Okay, very good. Uh, So this, I think, when I did a presentation on the path to AGI, I talked about Genie 3 a little bit. So I won't spend too much time. But Genie 3 is a model to create a dynamic world. This is a model from Google, and then Genie 3 can be used for has other applications. But so it's a world model capable of generating like interactive real-time environment from text prompts, right? So you text to say, okay, I want to visit a bridge in Ireland, and then it's going to create that universe. Or I'm going to fly from the Empire State Building, and it's going to create that universe. So you have, from text prompt, it's going to create that not only an image, but a sequence of images like videos, right? So it's what is doing. So it can be a navigation, so like 24 frames per second and 720 p resolution, so very realistic. So you can have also real-time navigation interaction, right? So you can you can navigate in real time in that environment, and there's a physical accuracy. I think what is the most striking is that this is not trivial to do. Plus, I think one of the examples they give is that suppose you enter a room, you paint, the wall is white, you paint the wall in blue, okay? Then you turn your back, so the wall is not visible on the frame, right? And then a few seconds after, you turn, you look at the wall again, right? And then you see the wall is going to be blue, right? So it has the memory of your past actions. Many previous models couldn't do that, right? You'll do something, you go at a frame, and then you go back to the frame, then it's as if nothing has happened, right? So this is kind of so this is kind of a consistency that you require. I know you play with like video generation. For instance, there's a you can do to create that for characters. But you have an image. But for instance, you create and you want to see you want to create a small video with one specific character. But if one frame, for instance, the character, you don't see the face, right? And you generate the video and the character shows the face is going to be different from the face from the previous images because the model had no notion that person has to be the same person that you've seen before, right? So there's a lack of consistency that Genie 3 is allowed to allowing us to do, right? Um, so there's a promptable world of events. So the user can alter the environment, create like what if scenarios, etc. So it can also that diverse capabilities, simulates natural phenomena, volcanoes. So you say, okay, I'm Hawaii visiting an active volcano. So the volcano is going to see, eject lava and so on. Fantastical scenes, reward locations. So this is very useful for gaming, but also for simulate, walk on the moon, visit Mars, and so on. So we saw Dreamer before and versus Genie. So what's the difference between the two? So you can see that Dreamer is kind of the brain, right? So so it's a reinforcement learning model that can learn the map to solve tasks and maximize reward, right? Genie 3 is like the playground, right? It just tells you, okay, when I move, what I'm going to see, right? But it's not telling you anything. What's the optimal course of actions to achieve a particular goal, right? So Genie 3 is the playground, Dreamer is the brain, and then the objective is to merge the two, right? So you have like agents which are like programmed by Dreamer, Dreamer style agents trained by reinforcement learning, living inside a Genie environment, right? And so then you don't have to to navigate yourself, right? To say turn left, turn right on the text prompt. The agent itself in there is going to evolve naturally by following a reinforcement learning algorithm by trying to maximize a sequence of rewards. So a reward could be survival. For instance, the objective would be not to die in the Genie world, Genie 3 environment. So it means that the agent is going to jump from a bridge or not to do anything risky, right? Or it could be collect a certain amount, if it's in a game, collect rewards or solve puzzles and so on. So the agent is going to evolve naturally, following an algorithm like Dreamer. I mean, this is
What you're seeing are not games or videos. They're worlds. Each one of these is an interactive environment generated by Genie 3, a new frontier for world models. With Genie 3, you can use natural language to generate a variety of worlds and explore them interactively,
the text prompt,
all with a single text prompt. Let's see what it's like to spend some time in a world. Genie 3 has real-time interactivity, meaning that the environment reacts to your movements and actions. You're not walking through a pre-built simulation. Everything you see here is being generated live as you explore it. And Genie 3 has world memory. That's why environments like this one stay consistent. World memory even carries over into your actions. For example, when I'm painting on this wall, my actions persist. I can look away and generate other parts of the world. But when I look back, the actions I took are still there. And Genie 3 enables promptable events, so you can add new events into your world on the fly. Something like another person, or transportation, or even something totally unexpected. You can use Genie to explore real-world physics and movement, and all kinds of unique environments. You can generate worlds with distinct geographies, historical settings, fictional environments, and even other characters. We're excited to see how Genie 3 can be used for next-generation gaming and entertainment. And that's just the beginning. Worlds can help with embodied research.
Okay, so the idea is that, I mean, they do that, it's not just for fun, right? It's that because it allows to train, especially like robots, right? So it's very useful for robotics. So you can create like very realistic environment, and then you can train the robot in simulation much faster than in real life. So in a factory, or on outer space, and so on. So this is very very important. Okay. So here, this is like another like a world model. So this one is comes from the Ruby team. I think from I think it's a company called Ant. They're based in China. So this is open source. So you can look at I imagine that you can look at the code, some of the data they use. So it's open source world simulator. So that bridge the gap between video generation and dynamic and interactive virtual environments, right? So there's real-time interactivity. It's very similar to Genie 3, right? But it is open source, long-term memory, for conceptual consistency, and versatile environments, right? It could be the different environments. So very similar to Genie 3, but this, because it is open source, you can read the paper. There's a paper on so they tell you exactly how it is it is done, right? So yeah, so here you can have a sequence of actions. So you can navigate, like we saw in Genie 3. You can navigate in a car and on a dragon and so on. You can have an input, right? You can image, or it could be text also, right? So, and then it will LightBot World is going to create the sequence of videos, exactly like Genie 3, right? Um, so so there's a different like, type of usually so they use so to train that is like large language model you need a lot of data. So they need a lot of like video data from different sources to do pre-training, middle training, on post training, on a lot of also captioning, right? Because it has to understand, you have to give some intelligence to the model so that it understands what it sees, right? So that's why captioning is very important. So captioning means that you describe the image, right? So whenever you have text and images, you need some training data with text and images, right? It's not magical, right? So okay. Uh, so here, yeah, maybe spend maybe just a minute on this. So data is very important, right? So there are it's a three-part pipeline here. The data engine. So this is what we call data acquisition, right? Uh, so it could reward video data, right? So first or third person. First means that from your point of view, POV, and game data. So game data is easy to collect, right? And synthetic data renders by Unreal Engine. Right, so Unreal Engine is an engine to make video games and so helps make movies, and you can make like virtual environment but which are like quite realistic and also verify like very physical constraint. Like you can go through a wall or so there's a bit of there's some physics in there. So that's very useful. So they collect, so they can do simulation of games and then collect the data, right? Um, then the second step in the pipeline is what they call data profiling. So they filter, standardize the data. So they try to extract the metadata, so the descriptive data of these videos. And but they also, because they need to tag these videos you need to add some text, right? So they will typically use a VLM, visual language models, right, to explain what is in the data, right? And also they sometimes you can also ask to describe a particular pose, an annotation, to annotate the data. Right? So today, for instance, the ChatGPT or Claude and so on, you can upload an image and ask Claude or ChatGPT, describe to me what you see in that image, right? So you can, so our models are kind of almost like, so they have the current chatbots, in fact, are already multimodal. They don't only understand text, they understand images. Right? So they use a VLM to annotate these videos, and then so this also so this is also the step of data captioning, right? So they do a full narrative of what's happening in the videos, right? So for example, if you see like videos of a car driving in a countryside, then so in the training data, then one it's asked to generate or show me a car driving in a countryside, and they will remember that you have seen it before, so you can know it'd be easier to generate this data. Okay, so that's how it works, right? So you always need a lot of data. So this is like what they call the captioning narrative, sensor caption on temporal. Okay. Another open source model. So this one is an American one. It's from Nvidia. So it's called, in fact, there are like two models. The first one is Cosmos Predict 2.5. It's 2.5 because there was probably a Predict 1 or 0 before, probably Predict 1. So they are also like they are also like world model. So Cosmos Predict. So it's also so it's a world model where you can prompt with either text with a text prompt, very similar to Genie 3. And you can text, but you can also add images. You can add videos, short videos, right? And then it will go into transformer based model, right? Uh, then transform this into some latent variables projected into text, right? So here you use some text embedding, and then it will use the text to generate the subsequent videos, right? For instance, here it says, so here the prompt, robotic arm walks over a large metal structure as bright sparks, intense light create vivid blue and white rays, thick smoke billows. Right? So this is what the video I want to generate. So I enter the text. I can add some realistic some images, but without this is optional. And then it could translate it. So either there's a one here in this case there's no conditioning image, right? So there's only the text, right? Or there is a conditioning image like here. So this is what you see in yellow. So one image can try to extrapolate. And the conditioning videos, the short videos that you see here, right? So it goes into to this model that will then it will generate so these tokens that we can transform into videos. Okay. So here this is a specific model called Cosmos reasons, where you can understand reasons. Why reasons? Because you understand the prompt, right? So that's why you need that reasoning model. Okay. And DIT is what you see typically in a visual language model. Right? So this is a Cosmos. So we have Cosmos Predict, right? So one text prompt or one image or one video, generate a short video. So Cosmos Transfer is something a bit different, a bit more sophisticated. What it allows you to do is to have more control on the image that you generate, right? And the way you control it, you can do either by text, but you can do things as sophisticated as okay, I have one. I take a picture of one person doing in a certain pose, and I ask the model to say, okay, I want to put a different person in the same pose, right? So this so it means that you had not only to understand the text, but you had to understand what's going on in the picture and to be able to replace that person with the other person. Because you join another another image, right? So you have more detailed control of what's going on. For instance, you have that person in a different that pose, and you say describe or make that person follow the pose in that other picture, right? So he has to be quite smart to do that. So here the pictures that these are different. Like here they compare Cosmos Transfer 2.5 to another version of the model and see how it is improving. For instance, here there's a prompt that says kitchen cabinets are highly polished bright red panels. And see the earlier model. Some of the panels are red, but some of the panels are not red. Right? But see the more recent versions, everything is red. Right? Here, I don't know what was the prompt or context, but here the earlier model was creating a picture. I don't see very clearly, like half a car. A car doesn't really exist, right? And then here also there's something weird with these cars, and the new model doesn't have that. Or here, it's a robot for simulation of folding clothes. A lot of folding clothes here, and you see that here you have the clothes on the edge versus the environment is very clear, right? This is the clothes, and there's a blue background, the blue sheet behind, right, that covers the table, but they shouldn't mix. But you see, like the previous version, it was mixing the two. So there's some like area which is half clothes, half sheet. It shouldn't be there, right? So this is what they call the edge control. So to evaluate, so in previous presentation, I often spend a lot of time on leaderboards or benchmarks. So here it's more tricky to have benchmarks, but there are a few. So one well-known benchmark is the physical AI bench leaderboard. So it's exactly designed to evaluate this world model, or they call it here physical AI systems. It is when it is in real life. So they try to evaluate perception, prediction, physical reasoning in real world scenarios, right? So they are like 2,800 real world cases, right? And so where they know what should be the answer, right? And so try to access the physical coherence, the visual quality, and the domain knowledge. So they have three different tracks for generation. So how good the model is at VGM, I think the video generating models, right? ML, probably multimodal or something like that, LLM. So evaluate these generating models' ability to predict future video frames, which are like physically plausible and consistent. Okay. Uh, then the second track. So this is what you see here, right? And you see the different. So there are different ways to evaluate this. No common sense. I mean, you have all the details, but usually different benchmarks. So these are for the generation track, a different way to evaluate and different scoring. Okay. And then you see the different models. So Cosmos Predict for Nvidia is very good. And you have VO3. VO3, I think, is also Google model. I suppose it is underlying Genie 3. I think Genie 3 and VO3 might be the same engine. Then behind that, you have another Cosmos model. One is a Chinese model also, right? So you see that different performance. And then you have different tracks, conditional generating. So it means that you have also control signals, right? So it's conditioning on the control signals. So you say, well, so not only generation, but does it react correctly with the different controls, right? I turn left, turn right. There's a consistency with that. And then understanding, right? So this is the third track. So they assess this model capacity to interpret and reason about physical rules from video data, right? So is it physically grounded? Are objects falling, vertically and so on? Does it model gravity and so on, right? So there's a consistency in physics. I mentioned that last time when I covered the path to AGI. So quickly, just like Fefeli has a startup called and she has also a world model called like a Marble. So here again, you input. You can try on the website. I think you can go to this link. You can on text, enter a single image, multiple images, video, 3D scenes. It goes into the model and generate a 3D world, right? So you create images, videos, etc. Okay. So I won't go through the video when we're running a bit out of time. This I talked about this, so I'm gonna skip this. The only thing just to mention that these world models are virtual models, but they're not real models. So there's always the question mark. Are these if you train a robot, let's say in Genie 3, right? You train it by reinforcement learning and so on, and it's very good in simulation. How is it going to behave in the real world, right? So that's why that simulation, that sim to real gap is important. If the gap is big, it means that something that works in simulation might fail completely in the real world. Also, so people are very concerned about this and make sure that the simulation are realistic, that the things are robust, and so. So that's the pros of simulation. Well, it's safe. You can generate a lot of data. It's very clean in terms of ground truth, and you can do it very fast. Right? You can do it in parallel and very fast. and very cheaply. The cons is that reality is very complex. So maybe like you cannot model it in the computer. Like let's say you want to model an AI agent to be air traffic controller. Okay, so you have to model, like it's a Genie 3. Let's say the recent example, LaGuardia Airport. Right, you have to have a realistic simulation of LaGuardia Airport with all the planes, the takeoff, landing, air traffic controllers giving orders, and so on. And given what has happened recently, you have to be sure that you have model also fire trucks crossing the path of a plane, right? Or this kind of environment must also be modeled. If you didn't do that, then the AI probably might never know how to react or what to give the. I mean, in that case, in real life, the human made the error, or only humans were involved, right? And still there was it was an accident. But you can imagine an AI air traffic controller who never seen a traffic truck crossing the path of a plane, but not know what to do, right? So all the complexity of the real life has to be modeled, right? On anything, nothing should be, hopefully at a sample. All the AI has to be smart enough to learn from this, right? So distribution shift means that sometimes the model will exploit something very specific to a simulation, right? It's like overfitting a model, right? So when you overfit the model, it means that out of sample in real world, it does very poorly, right? It just like took some quirks in the data and learned the behavior, but it's not really something that can be applied to the real world, right? Missing embodiments, it means that some physical intuitions are missing in simulation because not everything can be modeled. And there's also social and cultural gaps that might not appear in simulation. So here, say, if I give you the example of air traffic control, suppose the AI is working in a mixed team, like AI and humans. Right? So the AI has also to interact with humans, who might communicate with the humans, and the humans might react, might be upset or might be tired and so on, and the AI might not understand why the humans is not responsive. Maybe the humans haven't slept for the past 48 hours, so not responsive and make a lot of mistakes. But the AI, if the AI is not aware of that, right? Then it might not interact correctly with the humans and make mistake, right? So something that it has never learned in simulation. So in simulation means that to be realistic, a simulation has to simulate realistic humans with all their flaws. So simulate humans that a human has never slept in the past 48 hours, a human who forget things, humans who is angry, human that doesn't like AI. So all these things has to be in the world that you model. Otherwise, it'll be missing, and the AI might make a mistake, right? Okay, so limitation and challenges. So beyond sim to real gap. So we talk about this is the reality gap. So there's a complexity, right? Real world might be too complex for world modeling. A lot of uncertainty, right? So so maybe world model might assume that we know everything, that everything can be modeled, but maybe things that we don't know, right? For example, we not necessarily know how many planes are going to arrive, right? For a given hour, right? You can only see, you have radars only to observe what's happening in the neighborhood of LaGuardia, but suddenly you can have 70 planes arriving instead of 35 planes, right? So all this kind of so yeah, you might be under staff or overstaff, right? Depending on your prediction. Notion of scalability is that the world is much more complex, right? So the trained model might because you summarize everything into like latent space, and the scaling might not be possible, and generalization, right? So can you generalize what you observe in the world model to things that you have never seen, right? So let's assume that suddenly UFO. I don't know, there's a new term for that. I forgot. Like I say, a spaceship arriving on LaGuardia, right? And it is definitely probably not in the training model. Maybe in video games. Maybe it's in video games. I don't know. So what is the AI air traffic controller supposed to do, right? So they have to be able to generalize these kind of things. Okay. So more challenges. So the cost. These things cannot be done at home, or like you need very powerful computers. Nvidia can do it. Ant is a big company in China, so they can do it. But even a startup, I'm not sure if they can do it, because the amount of data is huge, right? It's talked about millions and millions of videos. So you have, we talk about partial observability. We don't observe everything perfectly. The data, the training, there might be bias in the data. Training data might differ from the real data, and so on. You have this distribution shift, right? So there's what you observe may be out of distribution, something that you have never seen, right? Rare events happening that you have never seen are not represented often enough in maybe something like three planes colliding at the same time, something you might have never seen in the data, right? So future research, so this very active field of research. I mentioned Fefeli has a startup, right? Is trying to do that. Yann Lequin from formerly at Meta in France, he has a startup trying to do that world model. So there's a lot of things happening, and why are this? So this is very interesting, very useful, but there's a lot of open questions on future research directions. So try to make these models smarter in terms of causal reasoning, right, to understand cause and effects. So a lot of it might be involved, like labeling the data, the videos. So you have to teach the machine this is causing that, right? And so they have to be able to learn that. Model uncertainty, continual learning. So these models, like the chatbots that you have today, there's no continue. They don't keep learning, right? They are trained once, so they are trained, every few months or every once a year, and then they stops. The weights are frozen, right? So there's no continual learning. Why? Because it costs a lot of money to train this model, hundreds of millions of dollars, right, to train this model. So they don't train them all the time, right? But at certain point, you might want to have future models to be able to learn as it goes, right? Uh, because the world is changing every day, right? So suppose tomorrow we have a alien invasion, right? So the first UFO will be something very new. But then maybe tomorrow we have like 10 UFOs or 20 UFOs, hundreds of thousands of UFOs, so day after day as the UFOs arrive on Earth. Right? So you might want the AI to learn from that, right? Say, okay, we get more CNN recording UFOs, arriving on Earth. So they have more videos are generated of people taking their cell phones and recording UFOs. So you might want these videos to go into the world models and the models to learn from it. So you want continual learning, right? So this is something that we want that. Interpretable world models to be able to inspect, query, and correct on these models to be corrected by human operators. But so it means that you have to be able to interpret the world models and why they're making this kind of predictions, and maybe to have more integration with physical priors, maybe to have objects to follow like physical laws, right? So it's done in so you have this physics in I think it's called PIN or something like that, physics implied neural networks. So you might want to integrate with that. And then once you have world models populated with agents, right? We talk about Dreamer on Genie 3. So you have multiple agents driven by reinforcement learning, living, permanently to real world, and how they interact, how they communicate. They might build like new world in there, a bit like what the kids do with Roblox, Minecraft, and so on. So you might have these kind of things populated with AI agents in a universe like Genie 3. Okay.